Okay, before we get into what inverse functions are, a little reminder about functions. Functions, you can think of them as machines that have input and output. So we call the x coordinate or the x value our input or our domain. Those are all interchangeable words that we use. And our output is our y value. It's our output or our range. There's three ways we express functions. Here's one way. We can have a table where we list our x values and then we list our y values. Remember, this column, the x column, would be called the domain, or we could call it also our input values. This column we would call the y column or our range or our output values. Okay, so again, this function is some type of machine. If we plug in 3, maybe we get out 7. Or in this table's case, if we plug in 2, the table says we get out -1. So a function's got an input and an output, a domain and a range, an x and a y. So now we're going to look at what is an inverse function then. Inverse function switches the input and the output. And again, we can use those other words there, x value and y values. Or we can use domain and range. So an inverse function will switch those. So if we look back at our table example, the inverse function, we would use this little notation, f inverse. It's a f to a -1 power. And it's going to be that same table, but we reverse all our x's and y's. So our y column now becomes our x column, and our x column becomes our y column, or our input and our outputs are exchanged, are switched. Two functions are inverses if their operations undo one another. So that's a key characteristic of inverse operations. Okay, that's what they do. They undo each other. You could think addition and subtraction here. Those are inverse operations. If I take a number and add 3 to it and then subtract 3 from that, I end up back at the same number. They undo each other. Addition and subtraction are inverse operations. Division and multiplication are also inverse operations. Square rooting and squaring a number are also inverse operations. All right, so here is a set of numbers, or x's and y's. We call that a relation. A relation is just a more general term for a function. So remember that in a set of ordered pairs, the first one is always the x, and the second one is always the y. So if we want to find the inverse of those, all we do is switch them just like we did on the table. So I switch each pair of x's and y's. And that's the inverse of our relation. These fancy brackets are just like a bag that's grouping all of these points, or it's holding on to them saying it's a set. Let's do it for B. Actually, you're going to pause the video here and try it for B on your own and see if you get the right answer. Okay, so here's what you should have gotten. You can pause the video again if you like and see if you got the right answer, same answer as I did. Okay, moving along. Let's look at how, if you're given a function, how can you find its inverse function? Remember that they want to undo each other. So here are steps. You want to kind of make notes on these or write them down. So step 0, you're going to rewrite the function in terms of x and y. So no more function notation when you want to find the inverse. You want to change your f of x's to y's. In the given function, switch x and y. So after you rewrite with y's and x's, you're going to then switch the x and the y, because this is the key step. This is the definition of an inverse, right? Switch the x and y. So now you have your new inverse equation. So step 2 is going to be solve that equation for y. And then we take out our y notation and we put back in our inverse notation. This notation is very important. It tells us something about this function. It says, hey, this is the function that undoes whatever f does, as g inverse would undo whatever g does. All right, so let's do an example. So if our function is f of x equals -3x, step 0 was to rewrite Get rid of that function notation and call it y. Now we apply our definition of inverses, which means switch the x and the y's. Then the next step is I want to write it as y equals. So if I solve for y, this is negative 3 times y. So I'm going to divide each side by negative 3. And I get negative x over 3 equals y. So I'm going to rewrite that up here as y equals negative x over 3. I know we're dividing by negative 3 here, but I'm just going to put that negative out in front of the division. Then we rewrite it in function notation. So we're not going to call it f of x because this is the function that undoes f of x. So I've got f of x. This is now the inverse function. So let's take a look at what that means. So I've got f of x here, negative 3x. I'm going to put that in a box like it's our function machine with input and output. So if I do the composition, if I pick a number, let's say 2, and I put 2 into that machine, I plug it in for x, I get negative 3 times 2, it spits out a negative 6. If I take that answer and now put it into our inverse machine, I put that in for x in our inverse machine, I get negative 6 divided by 3 is negative 2 times the negative sign becomes a positive 2. So you can see that this inverse machine undid what the other machine did because I end up back at the same answer where I started. That's what inverses do. Let's try to find the inverse of g here. So step 0, is to rewrite with y's and x's. Step 1, that's applying the definition of an inverse. Switch the x's and the y's. Now you want to solve for y. So the first thing we're going to do here is we're going to add 6 to both sides of the equal sign. So I get 4y equals x plus 6. Now I'm going to divide by 4 on both sides. Got to divide the whole side by 4. So that means I get x plus 6 divided by 4 equals y. If I rewrite that, I get y equals x plus 6 divided by 4. And then I use my inverse notation on the final step. Again, we don't want to call it g of x because it's not g of x. It's the inverse of g. It's going to undo whatever g did to a number. So if these are our two functions, let's plug in a 2 again into g of x. What do we get out? If I plug in a 2 and I plug that in for x, I get 4 times 2 is 8. 8 minus 6, it spits out 2. 2 is a bad example. That's going to get confusing. Let's go with 4. If I plug in a 4, 4 times 4 is 16. 16 minus 6 is 10. So I plug in a 4 to g, it spits out a 10. If I now take that 10 and plug it into the inverse of g, I get 10 plus 6 over 4. That is 16 divided by 4. It spits out a 4. So you can see I'm back to where I started. Okay, this last one, if I change my h to a y, I'm now going to switch my x's and my y's and then solve for y. So I add 3 to both sides. And then to solve for square, I square root to undo the square. So then I get y is equal to plus or minus the square root of x plus 3. That creates two equations. And I'm going to rearrange this and write the y first. I get y equals the square root of x plus 3. And I also get y equals the negative. I get y equals negative the square root of x plus 3 because I have two versions. So on this one, when you do the inverse, you're going to have to get two different functions and two different equations, and it's not actually a function because that breaks the definition of function, which we haven't really talked about much. So whenever you have a squared, it might be enough for us for right now to just stop right here. Because we're not going to be able to really write it in function notation anyway. So this step would be okay when we have squareds. All right, how do you determine if two functions are inverses of one another? If you want to see if they're inverses, you have to do the composition and see that you get back what you started with. And you have to do it in both directions. You have to show that one undoes the other and the other one undoes the other one. So if we look at f of x and g of x here, if I do f of g of x, I want to show that when my input is x, And when I do the composition, I end up getting back to just x. So let's do that. F of g of x is f of x plus 7, because g of x is equal to x plus 7. So I take g of x out and I replace it with x plus 7. So f of x is x minus 7. So f of x plus 7, I'm going to remove the x here. Right, I'm taking that out and putting a placeholder here. And in its place, I'm putting x plus 7. So I get x plus 7 minus 7. If I simplify that, I arrive at just x. So I showed that the composition comes back to x. The input was x, and the final output comes back to x. That shows that f undoes g. I put x into the function g, and whatever I got out, I put that into f. F undid that. Now we're going to show that g undoes f of x. So if I take the function f of x, that's the inside function there, right? F of x is on the inside. If I take that and I plug it into g for x, I'm going to get g of x minus 7, because I'm plugging that in, is x minus 7 plus 7, right? This part, I take it out, I put the parentheses, and in its place, I put x minus 7. So if I simplify this, x minus 7 plus 7 is equal to x. So that's how you check if two functions are inverses of each other. So yes, they are inverses of each other. I got x both times I did composition. Let's check if b are inverses. Let's do f of g of x. So f of x, g of x is equal to 3x minus 2. That's the inside function. We're going to plug that into there. So 1/2, I take out the x out of the outer function f. I remove that x, and I put a blank placeholder. And in that placeholder, I'm going to put this entire function. All right, so now I've got to simplify this down to x to prove that it's the inverse. So it looks like distributive property is going to work here. So 1/2 times 3x is 3/2 x. 1/2 times negative 2 is negative 1 plus 3. If I simplify further, I get 3/2 x plus 2. I can't do any more simplification. It did not simplify down to just x, so they are not inverses of each other. Okay? Let's look at these. These are actually inverses of each other. We want to see what it means graphically when two functions are inverses of each other. So we're going to look at this set first. I already have it typed into Desmos. You guys can pause the video here and type in those first two functions that you see. I have them all ready to go, but these are the first two. So you want to just type in those, pause the video. Okay, welcome back. What does it mean on the graph to be inverses? Well, remember we're switching the y and the x. So let's look at, I'm going to turn on the line y equals x. I'm going to make it dotted so it's different than the others. If I turn on the line y equals x, you can see that our functions here that are inverses of each other, they're reflexive. If I flip that blue line over the line y equals x, if I reflect it, I'll get the orange line. So they're a perfect reflection of each other over the line y equals x. Let's look at the other two functions. So I'll turn those off, and you can pause if you like and type these two in to your equation, to your Desmos. You can see that those are the reflection of each other. Whoops, I want to turn that. Okay. Over the line y equals x. What happens is we just don't see the bottom half of the sideways parabola because we want functions. But that blue parabola, if I reflect it over the line y equals x, I get the sideways orange parabola. But we want these things to be functions past the vertical line test. So the bottom half of that function, we're not going to graph it. We just take out that bottom half of the parabola. Lastly, the other two functions that are inverses of each other are lines again, and you can see they're reflexive over the line y equals x. So what does it mean graphically to make two functions inverses of one another? They are reflexive over the line y equals x.